to my second set of slides. So I've talked about the structure and behavior at the most basic level, kind of the syntax and semantics associated with these sorts of models and the diagrammatic mechanism. And now we are equipped to start talking about the challenges of infectious disease modeling and the idioms of infectious disease modeling, of which there are many. And so for most people in here, they will have encountered before the granddaddy of all Kendrick-McCormick models, or the grandmother of all, the susceptible infectious remove model introduced by Kendrick and McCormick nearly a century ago in 1927. They followed Ross's work on malaria with work dealing with human-human transmission. And the basic structure of the model with, a little bit of elaboration, I put in immigration, for example, here, is as follows, right? So we have a susceptible state variable and infective and recovered. And we have, you might guess here, and if so, you guess with good reason, a first order delay coming out of infection, an average duration of infectiousness, and infective, the recovery is given by infective divided by the average duration of infectiousness, as you'd expect. But what we see here is a structure that is more emblematic of communicable disease modeling, involving a situation where this flow, the incidence, instead of just being governed by and limited by the upstream quantities, susceptibles, like recovery depends on infectives. You ain't going to get anyone recovering if there's nobody infective. You ain't going to get anyone getting, contracting COVID-19 if there's no one susceptible to it. But it also depends on infectives here. And so this flow is going to be dependent on two state variables in a way that marks it out as nonlinear. And that's going to have huge implications for the data science side.
Dr. Osgood,
yes.
Are you, you're not sharing your screen. Is there
I'm
something
not sharing the screen.
Seeing?
Oh my gosh. I'm so appreciative. There's got to be like part of my brain which is missing a lobe associated with Zoom screen sharing. Thank you. Thank you, Jalen. I recognize the voice. So thanks for the heads up. What I had shown is this model here. Is focusing on this as a first order delay, and then this is definitely not a first order delay, and emblematic of communicable disease models because it depends non-linearly, as it turns out, on both susceptibles and infectives. It takes two to tango. We'll get no infections unless we have both susceptibles and infectives. We could have all infectives and we get no incidence because we have no susceptibles, or we could have all susceptibles and we'd still get no infections without infectives. Okay, now models, we're going to be speaking about this in terms of pathogen transmission. It does bear note, and some observers have made great use of the fact that contagion is a phenomenon that extends well beyond pathogens. And for those who saw Josh Epstein's talk on the mutual contagion of fear and pathogen, will recognize this. And much of what we see in terms of COVID-19 pandemic can be argued fairly convincingly to exhibit not just one contagion, but several, and ones concerning risk behavior that are shaped by perceptions of risk also being communicated from one person to another. So within this sphere, we're going to take our model that we just introduced and introduce some classic state variables. So S, we're going to denote the number of susceptible individuals. Sometimes it's given, like in that diagram by Garnett, it's given a designation X. We're going to have a designation for the number of infectives, the number of recovered individuals, and very commonly, when we have a population that's closed, we'll give a name for the total population. I should have been more careful with this to emphasize here that n is in this particular rendition, n is a dynamic variable. In other words, it does depend on the state of the model. It's s plus I plus r, and in fact, it's changing because we have people coming into the model. In the classic Kermick-McKendrick model, you would have no immigration and n would be a constant. And in fact, representing r is elective because r is just given by n minus s minus I, or n minus quantity s plus I. But let's unpack this, right? Using this idea that we saw before, that each state variable can be turned into an element of this differential equation. So with the rate of change of s, how quickly s is rising or falling, 10 people per week rising, or 3 people per week dropping. This is m, this is the flow in, and this is the flow out of s, right? And so we have these two terms here. This should be familiar from my earlier lecture, and again, expunge the a, out black a. Okay, so a model like this will, a model like this, and in fact, a system like this, such as we're abstracting, will tend to exhibit, a characteristic set of dynamics. We talk about structure driving behavior, and so it is with a model like this. And based on its initial conditions, it will tend to exhibit behavior that will, and its parameters that will differ some. But characteristically, it will include a spread of infection. So this is I is the red one. We start with very, very few people infected, and they they infect other people by exposing them here. The more infectives there are, the greater the chance, the greater the hazard rate, the probability per unit time that a susceptible will get infected. And as a result, it will lead to more and more people becoming infective, which will breed more infections. So you get an exponential rise initially, and then you get a plateauing as recoveries come to match incidence, and then you get a drop as in turn we get more people recovering than are incident. The fuel for the fire has been largely used up. There's fewer and fewer susceptibles around. Each infective is less and less efficient at finding people to infect. More and more of the people around them are already have already been infected and can't be infected again. And the number of people recovering exceeds those coming in. So I is becoming smaller. I is becoming smaller, and each person is communicating to fewer and fewer, and it tends to drag the state down. I'm confining my comments when m is 0 here, but when m is not 0, it'll tend to be like shoveling firewood into the fire, which will keep it going. And the number of susceptibles tends to drop, but it isn't drained entirely. And the number of recovereds, whatever its initial value, it'll tend to rise up to a higher level. This is again for no births and deaths. We have a set of standardized parameters for this, including the key ones shown here: contacts per susceptible per unit time. The units associated with this are 1 over time. And that's this one here. We have a beta parameter, by contrast, which is a probability. So it's unit dimension. So it or as might sometimes be called, dimensionless. It's independent of unit systems. The contacts per susceptible will change whether we measure, our time in weeks or days. How many contacts we have per unit time will differ. That's not the case for this probability. Probabilities are invariant of units, and this is a for each discordant contact between a susceptible and an infective, what's the probability will transmit for that. Now, what I want to draw you, we'll come back and explicate this term later, but I want to draw your attention to a foundational fact for this course, or fact that will be very important, which is, while we were dealing in my first set of slides today with linear systems whose behavior depended linearly on, was just a constant times the state variables. We are entering now a new regime. Well, okay, I'll show it here, where we're depending non-linearly on state variables, and there's an S times an I term here. Previously, and you can look at it for recovery, someone's chance per unit time of recovering, if they're ill, their chance per unit time of recovering is fixed. It doesn't depend on the state variable. They maybe have a 10% chance. Maybe their mean time infectious is 10. So their chance per day of recovering is 10% per day, right? 0.1 probability per day of recovering. So regardless of the time of the model or the state of the model, that's true. By contrast, for this infection transmission, a given susceptible chance of getting infected, their hazard rate of getting infected, their probability per day of getting infected, is not independent of model state. It depends critically on the number of people infected. If there's no people infected, they're going to have 0 chance of getting infected. If there's no infective circulating out there, they're going to have 0 chance. By contrast, if nearly everyone in the population is infected and they're the sole survivor, then they're going to have an extraordinarily high chance of getting infected. So in a nonlinear model, the behavior of the system in terms of the chance per unit time of transitioning, the rates associated with these flows in terms of the chance per, in this case, person per unit time of going is highly dependent on system state, and that's going to make all the difference. And to highlight this from math, I'm going to jump into something that I apologize for its kind of a full-on character, but for those from more mathematical background, you'll probably take away quite a lot here. Others will want to follow along in a rough way, but you'll appreciate, I think, the punchline. The basic deal is, when we have a linear system, we have flows depending linearly on state, and so we can express a system like this in terms of a matrix times the current value of the state. So the rate of change, that's what this is a matrix times the current state. Okay, and that matrix is invariant of system state for a linear system. There's some particular fixed rate of going down this path or any other path in a linear system. It's just a fixed rate. And so if we know the number of people here and we want to just get this flow, the rate of change of I is just this times I, draining out, and mu times or I divided by mu for the flow out of this and the flow into that. So we can express the rate of change of system state, that's what this S dot is, as a matrix times the current value of state. And it turns out that an implication of this is that you can decouple this system. So if we have a system where we have a set of these stocks and a behavior that depends linearly on that state, we can always transform it into a system which can be expressed as a set of independent stocks and flows, sets of stocks and flows, one for each state variable. And this comes through doing what's called diagonalizing that matrix, okay? And it's a lot of fun for those who are mathematically inclined, but you can, if you have a system whose rate of change is dependent linearly on the state with some matrix, this is the Jacobian matrix, we can solve it by expressing its solution as something like this. And this has a matrix in the exponent, which is can be kind of explicated as something like this. So this is a sum up of matrices. So this e to the jt is itself a matrix. And it turns out with a linear system, what you can get out is something where that system's evolution just it has a set of normal modes, and in each normal mode is captured for a given state variable, and you get an evolution of the system which is decoupled. There's no inherent coupling in a linear system, is what this is saying. We can always diagonalize it in a way that there's no deep coupling, that we could treat it as a set of independently evolving systems. And what that means from a data science perspective is we can kind of analyze each as a solitude and get a lot of insights. And those who are mathematically inclined could follow these slides later, but it's all very nice with a linear system. It all falls out and we get a bunch of normal modes, each independently evolving, and each has a stability criteria for whether it's expanding or contracting, and the situation is good, and the sun shines and the birds sing and the flowers open up. It's all very very nice. I didn't include the flowers and the sun and the birds here, but maybe for a future set of slides. So here we have a beautiful situation where what seems like a tangled system initially, a system with lots of intercoupled stocks and flows with all sorts of flows to each other, if those are all linear flows, it's full and sound of fury, but at the end of the day, it can be turned into a set of independent solitudes as systems, these normal modes, each associated with a normal mode. Now, when we're dealing with nonlinear systems, all that goes out the window. We still use linear tools in specialized cases like around equilibria. But in nonlinear systems, which are most systems, someone once quipped talking about nonlinear systems is talking like about non-elephant animals. Like most animals are not elephants. Most systems are nonlinear. I think that's actually a little bit overstating it, because if we take a microscope, when we look at any one point in time, we can treat a nonlinear system pretty well for the next little bit as evolving linearly. But it is true that we have to grapple with nonlinearity centrally for most systems. And for hard problems in the world, like dealing with COVID-19 or dealing with any number of challenges worldwide, we're dealing with systems that are intrinsically nonlinear. And that makes all the difference in terms of how we characterize them and in terms of how we analyze data from them. So within a system that's a nonlinear system, like an SIR model, an infectious disease model, we have these terms which depend non-linearly on the state. What do I mean by that? Well, before, when we had a linear system, it was a flow that was linear, just was some constant times the value of a state variable. But with a nonlinear system, we have this S times I. And again, that means if S is 0, doesn't matter what I is, this flow will be 0. If I is 0, it doesn't matter what S is, this flow will be 0. You need those two to tango. It can't be decoupled to just deal with S separately from I. No, we have to deal with both together. Now, one thing this is going to also lead to, which has profound implications, is that the data for S tells us about I, or the data for how S is changing tells us about I. and how, I is changing tells us about S. And for deploying the lens of data science, that's going to be really valuable. So with nonlinear systems, we can't express a system in a linear way. We can't just take it apart into nice pieces, each of which we deal with in isolation, and then assemble our understanding for the behavior of the whole from those pieces. Instead, we are stuck with this intrinsic entanglement, this hideous sort of twisting together of the system. And for those who are mathematically inclined, that Jacobian, which characterizes how the rate of changes of the system depend on each state variables, is not a constant. It's not a constant matrix. It's a matrix whose entries depend on system state. The rates depend on, the rate at which someone gets infected depends on the number of infectives or what have you. So we can't decouple the system. And this does mean, though, that when we're looking at these systems, what we get out of one piece of the system speaks to us, whispers to us, hints to us about what's going on in other areas of the system. It does mean we can't reason about the behavior of the system as a whole by just summing up about its pieces. We can't, through some clever transformation, just deal with the pieces and not have to worry about the whole. We have to deal with the whole elephant, folks. And we have to, we have to do so in a way that attends to the fact that the behavior of the system as a whole can be very different from those pieces, and each piece in isolation. We can't decouple the system into a natural coordinate system that holds at all times. And we can't assume the system as a whole is the same dimensionality as its kind of nominal dimensionality. It will often, because of this entangling, have behavior that's actually quite a bit simpler or quite a bit lower dimension, meaning it has fewer degrees of freedom than we would otherwise think. So we are dealing here with nonlinear systems, systems that are nonlinear in a way that's going to lead to differences in behavior that require us to simulate them rather than solving them in closed form, and which will require us to, and which will open the avenues for us to learn about all pieces of them by listening to data on certain pieces. Okay, now having said that, and mindful of the fact we only have a few more minutes left, I want to unpack this term, which will be new to probably about half the class, this nonlinear term. I threw it out there. I said, something like this is the classic form, and it's true, but there's tremendous intuitions and tremendous value to enhancing those intuitions or developing them for understanding models like this. And what looks to be a kind of fearsome gobbledygook of Greek and Latin letters turns out to speak volumes. So I'd like to talk about this. We noted it's a term that multiplies S and I, and it's fruitful to approach it in one of two flexible ways. To look at it as a term, if we think about first order delays earlier, where we kind of had a chance per unit time, alpha of progressing times the value of the state variable, it's fruitful to think about this as some kind of probability per unit time times the value of a state variable. And you can do this in two ways, either with S or I. Let's do it with S at first. If we look at this is kind of C times I over N times beta. We could think of that as some probability per unit time collectively. And it's times S, times the number of people in this state. So that's the C times I over N times beta is like this chance per unit time a given susceptible will proceed down this path, right? It's their force of infection, it's called, this force of infection. And so that force of infection is a chance per unit time, say per day, a susceptible will get infected. It can be also treated as a, we might choose a different unit system per year for, a less highly communicable illness. The force of infection is one of the key quantities we use when reasoning about a model, and if it's something that is greater than 1, that will mean your average time in this stock is less than 1, right? Remember we said that the mean time in a stock is the reciprocal of the chance per unit time of you progressing. So if I have a chance per unit time of progressing of, let's say, 0.1, my mean time in this stock, so it's, let's say, 0.1 per day, my mean time in the stock will be 10 days. So if this value of this force of infection is greater than 1, it'll mean my mean time in S is less than 1. And in general, your mean time in it at any one time will be 1 over the force of infection. That's kind of a nice intuition to have. So if we have a force of infection of 0.5 days, 0.5 per day, it will mean your average time before getting infected is about 2 days if you're susceptible. If your force of infection is 0.01 per day, it means your mean time before getting infected is 1 over 0.01, which is 100. Okay, but let's unpack this more, because there's each of these terms means something. I over N is the fraction of the entire population that's infective, right? C is the number of contacts each susceptible has with anyone per day. So here, if we have C is the number of contacts a given susceptible has with anyone per day, and we multiply that times I over N, then what we get is the average number of infectives that a given susceptible will come into contact with per, let's say, day, per unit time. So C by itself, let's suppose each susceptible has contacts with, 10 people per day, right? And let's suppose half the population is infective. We have a total population maybe of 1,000, and of them 500 are infected, God forbid. Then I over N is 0.5. And so if you consider a given susceptible having contacts with 10 people per day and half the total population is infective, so this is 0.5, then that susceptible will come on average into contact with 5 infective people per day. You have a total of 10 contacts per day, but only 50% of them are with infectives. And then we multiply that by a per chance probability of getting infected to get an approximation for. Tends to work well when beta is really, really small, for example. Approximation for the total probability they will have been infected during that day per day. So each of these terms makes sense. C by itself is the contact rate of a susceptible with anyone. C times I over N is the contact rate a given susceptible has right now with infectives, number of infectives per day they're seeing, times beta. It's kind of an approximation to the total probability they'll get infected per day. And then you multiply that times S, and you get the number of people going down here per day. C times I over N times beta is the force of infection. The probability per day people will get infected. As such, this is a fruitful way to look at it. It turns out that there's an alternative way to look at it, which is, in my view, equally nice. This way is kind of the susceptible centric way. We're thinking about each of those susceptibles, and we're asking what's their chance of getting infected? How likely are they to dodge the infection per day? What have you, or to get infected per day, right? Something that's of concern to all of us probably these days. Okay. Now, the other way, though, is an infection centric. It's really asking for this infective, how many people are they infecting per day? So we have this formula here, but we can rephrase it. Just, hey, look, S and I are just multiplied by each other. Let's, instead of having S outside and I inside, let's pull I outside and put S inside, right? And so we just exchange their positions. We take into account, we take advantage of the commutivity of it. We can braid them. We can rearrange them. And this too has a very pleasing intuition, an intuition that is recommended not only by beauty but by truth in terms of its meaning. So here we have I times S times I over N times beta, S over N being quantity. So S over N is a fraction of susceptibles in the whole population. C is the number of people that each person comes into contact with per day. So if we have each infective, they're coming into contact with C total people per day, but only a fraction of them, S over N, are susceptible. So they're coming into contact with C times S over N, susceptible people per day. And for each of those susceptible people per day that this infective is, into which this infective is coming into contact, they have a probability beta of infecting that person. So maybe, the first person they come into contact with, they have a probability 0.2 of infecting them. The second person, 0.2. And maybe they come into contact, maybe they have a total number of contacts of 10 per day. Only half of them are with susceptibles, so that's 5 per day. Each one is conferred a probability of 0.2 that they'll transmit. The infected will transmit to this susceptible, unlucky susceptible. And so 5 times 0.2, or 1 person per day on average they're infecting. This term here, C times S over N times beta, is the number of infected people, number of susceptibles people being infected by a given infective per day. So C times the fraction that are susceptible times beta kind of gives us this number of infective people, number of people that each infective infects per day. And that's a very useful lens, a particularly useful lens in understanding the dynamics, because what it shows us is the central position here. The absolutely central position associated with the fraction of people that are susceptible, S over N. If the number of people that are susceptible population falls, and the fraction of people in the whole population that are susceptible fall, it will lower the number of people that each infective can infect. If it falls by a factor of 2, it will lower by a factor of 2 the number of people they can infect. And this highlights kind of the limiting character of the number of susceptibles. It becomes harder and harder as the number of susceptibles dwindles for each infective to infect as many. So that's another view of this term. This term has these 2 different views, which are very useful. And this fraction that are susceptible is this key throttle that plays this huge role within the context of infectious disease epi in helping us understand the dynamics and helping us to reason about why we're seeing the behavior we are right now, and why outbreaks such as that from the fearsome Omicron surge right now inevitably peter out when they confer some measure of at least somewhat persistent immunity. And, we could think of the number of the susceptibles as kind of fuel for a fire. And as the fraction of susceptibles that remain dwindles, there's less and less fresh wood for the fire to burn, less and less fuel for the fire, and therefore a smaller burning rate. And inevitably what will happen is the infectives won't be able to infect enough people that incidence will keep up. Recovery will equal incidence, and then the number of susceptibles is pulled yet further down. And so incidence will grow lower than recovery. Recovery will drain this stock. It will start pulling this down because the outflow will be greater than the inflow. And the number of infectives will shrink, which will even lower incidence, even as the number of susceptibles shrink. And we get this, drop in the number of people that remain infective, and that begins the climb down to a situation where the number of infectives is far smaller, or number of infectives is far smaller. So I've described some of the essential components of communicable disease models here. Their nonlinearity, the fact that they are coupled in this intrinsic form. I've tried to communicate some of the key concepts here with force of infection in terms of understanding this nonlinear term from two perspectives. Next time, I think we'll talk a little bit about the force of infection and the basic reproductive number, which falls right out of these equations, together with reasoning about the length of time people stay infective, and maybe one or two other things in the communicable disease modeling area. And then we'll be ready to start speaking about some of the, proceeding with the course beyond communicable disease modeling. Beyond just rehearsing or rehashing the basics of communicable disease modeling, to how we can use the tools of data science and constructs such as state space lens to understand and to inform us about this behavior on an ongoing basis, and to correct model understanding on an ongoing basis. So next time we'll finish up our kind of review of some of the basics of infectious disease modeling, and plow on to some other components of the course. So thank you very much for your attention. I again have gone over time, but I